Thank you very much for that kind introduction, David. It's a real pleasure to be here today. I should say it's also a little bit daunting. I'm not going to talk too much about the detailed science I do. What I want to talk more about is the motivation. I'll give some examples of the science I do, but it's more around where we're trying to get to and why. And as David said, I'm going to talk about solar, but I'm not an engineer. I'm a chemist. Originally, I was a physicist by background. And what my research around is looking at new materials which may enable new ways to harness solar energy going forwards. So I'm more a fundamental scientist. What I want to talk a bit about is just very briefly about where solar is going globally and why that's exciting. I'll then want to talk about two more technical topics. One is where we might go beyond silicon solar cells and how that might be interesting and what the challenges are. And then turn more to chemistry and think about how we can use chemistry to make sustainable fuels and chemicals, which is often called a process of artificial photosynthesis, essentially doing what nature does with photosynthesis, but in an artificial context designed to meet our energy needs. So that's the rough talk. I won't talk for too long. As David said, I should be about half an hour to allow time for some discussion. I've worked on solar. Why is it not going forwards? I've worked on solar. There we go. Pretty much all my life. And I've always been excited by sunlight because we have a lot of it. This is quite a classic picture of the solar installation on the planet versus up here, for example, our known coal reserves, our known uranium reserves. This is how much solar energy plants convert into biomass. This is the total solar, the total wind resource, for example, globally. The point is there's a lot of solar. And if we're going to be moving away from fossil fuels to renewable energy, then by far the most scalable renewable energy source we have is solar. And solar is getting cheaper. This is a picture actually from a paper published by Way et al. A couple of years ago from Oxford, where they looked at the trajectories of the past trajectories of a range of different technologies. And what's striking here, this is a log scale, and this is the cost essentially of different energy technologies. Yellow is solar, and it's come down in price over the last decades by something like 3 orders of magnitude, which is significant. And of course, that change in cost has driven the growth in solar. Currently, for the last 20 years or so, solar has grown by approximately doubling in capacity every 3 years. So it's exponential growth. Exponentials have a way of getting carried away themselves, and what starts off small can become very big. And I'll give you some examples of that. In general, solar has continued to do better than everyone expected. I quite like this a picture here, which actually was published in The Economist last summer, which was taken again from this Way paper, but it's a way of illustrating how the black points are how much solar was added each year. And the yellow are the predictions of where solar was going to go by all the different energy agencies, the UN, the International Energy Agency, all the economists and all this sort of thing, predicting where solar was going to be going forwards. And what you can see is that the growth has been going up, and yet all the predictions said that pretty much we've reached capacity and it's going to stop growing anymore. So this is, for example, 2021. The prediction was that by 2030, we would be here. The reality is that by 2024, we'd gone way above the prediction in 2021. We actually met that prediction within 1 year, rather than 9 years, and growth has continued. So essentially, all the economists and all the predictors so far have grossly underestimated the potential of solar, which is why for many years, the UK government essentially ignored solar as being a significant role to play in UK power generation. They've now changed their mind. Another way of drawing this is these are log linear plots of historically what solar's done. Wind is the same, actually, and battery. They're all expanding exponentially. And if you just take historical growth and take it forwards to predict where you might go, you can see that rather quickly we end up with quite large numbers. The only real question is when solar stops growing so fast. And so far, it's showing no signs of stopping. There's various predictions here of what might happen. The blue one may be the most optimistic one, but even that is saying that solar is going to start saturating in about 5 years' time. This is, again, a picture from The Economist of what will happen if solar carries on growing the same as it currently has for the last 20 years for the next 5 years. It more or less is saying that by 2030, and certainly by 2035, solar is going to be the dominant energy generator globally in terms of at least electrical power generation. And that's quite exciting. Of course, we live in uncertain times, and politics is getting even more uncertain, and renewables aren't always so much in favor in certain parts of the world. But what's driving this growth is no longer subsidy or policies. It's simply because solar is cheap. But the growth, the UK no longer subsidises solar. Most parts of the world do not subsidise solar, at least not significantly more than other energy technologies. But because very often solar is the cheapest pathway to generate power, it becomes the dominant pathway to generate it. The UK is a bit odd, actually, because, of course, today's sunny, but the UK has, in general, relied more on wind than solar. We're a windy country. But that's actually an anomaly. The UK is unusually windy and rather less sunny than many parts of the world. And of course, that's not the only answer. We have to think about how we're going to store, and I'll come back to that a bit later. But I think it's quite exciting that the pathways towards reducing our dependence on fossil fuels are in some ways already embedded, at least for electrical power generation. The UK government is starting to wake up to this. So the Tories, a couple of years ago, published various plans, which essentially are saying they want to increase solar by 2035, but fivefold. The Labour's evolved that slightly. They're going to increase solar by threefold by 2030, which is more or less the same thing. And so that's quite exciting. The problem is that the government says that's what they want to do, but they've done very little to actually work out how to do it. And that's maybe not an unusual problem of our politicians. And already we start to get worries that a lot of solar is PV cells going into large PV installations on arable land in the UK. Elsewhere, it's not always on arable land, but the UK hasn't got a lot of land. And how we're going to increase the number of solar cells fivefold without covering a lot more fields in solar is starting to raise concerns. And that, I think, is something we need to take quite seriously. If we look at what solar cells we have now, then almost all solar cells now are made by crystalline silicon. These were developed over 70 years ago. Essentially, they're made by taking a crystalline silicon ingot, making it very pure, because silicon is not a very good light absorber, actually. So you need quite thick and therefore quite pure silicon to make solar cells. But anyhow, you slice up this silicon ingot, and then you make your wafers, and these wafers you then dope and you make them into modules. And these are wonderfully efficient. But the efficiencies of silicon solar cells are about 27%, which is close to thermodynamic limits. There's a thermodynamic limit because the sun's what we call a black body radiator. It emits lots of photons on all different wavelengths, while a solar cell can only really be optimized for one output voltage. And so that limits the efficiency to about 27 or 20, I think 28% for silicon cells, what would be the optimum. And the modules now maybe about 22%, which is getting pretty good. And they're stable and they're cheap. So that's fantastic. The problem is that these silicon solar cells are kind of a one size fits all. The easiest way to put them out is to put them out in fields, in big panels, and that's all working very wonderfully. This is an a sort of summary of where solar is today. But the figure's slightly out of date, I apologize. That was when I actually was starting my research. That was my son outside his school. He's now 28 and is on site taller than that solar powered parking meter in Wandsworth. And this was even 10 years ago. This is where solar is. So I'm increasingly reaching the stage where the cost of the solar is no longer the cost of a solar cell, and where we start to have to worry about where we're going to put these solar cells. And that's meaning that we're starting to think about other ways of doing things. If we want to make things even cheaper, we've got to find ways to make solar cells which are, for example, more integratable. We need to think about how we're going to store the energy. We need to think about ways we can put the solar cells out and not displace arable land. One example here is our transparent PV windows to go into tower blocks, office blocks, where you can imagine you've got translucent windows generating power from, for example, near infrared light and letting the visible light through. We have the same idea here, that thinking about how we can integrate PV with plant growth. In the UK, we need all our sun, and so we don't tend to think about that. But a lot of parts of the world, they have too much sun. The plants can't cope, and we can think about how we can integrate PV and solar cells, and that's all interesting. One of the interesting points here you can see is this is a transparent solar cell, which is not possible with current silicon technology. This is another example. I'll skip one actually. Oh God, I missed it. This is something I get quite excited about. If we could cover the roof space, if anyone goes up a motorway now, they'll see big warehouses going up. These big warehouses are something like 80 million square meters of south-facing roofing. If we covered those in solar cells, that would generate, that would more than double the UK's PV capacity. So that will go a long way towards already starting to meet Labour's ambitions for growing solar generation in the UK. But of course, if you look at all these warehouses, hardly any of them have solar cells on. And it's simply because the current solar cells are too heavy. Silicon wafers are very fragile. They have to be protected by plates of glass to stop them bending and cracking and breaking. You can't put 2 plates of glass on a warehouse roof, at least with current warehouse building. But the warehouses are built much too light to do that. And so it doesn't work. And what we need, in this case, is an example. We need solar cells which are flexible weight and light enough to be able to put onto roofing. And so this is driving what I find quite exciting, is the idea that we can make solar cells different ways. I'm interested in printing solar cells onto flexible substrates, using a new generation of semiconductors which are based on solution processable semiconductors, organic and cross-cut material. So it's the idea we can print thin layers on some flexible substrate and do that in order to have a lighter weight solar cell. This involves new sorts of materials. I didn't say at the start, I should have done. I've been leading a Centre for Processable Electronics at Imperial for the last few years, the last 10 years actually. And this is looking at ways we can process semiconductors from either by some molecular evaporation or more cheaply by solution processing, by wet chemistry over large areas. So essentially the idea of painting solar cells is not quite that simple, of course, and not quite that easy. But this is happening, and these solar cell efficiencies in the labs are now approaching the same as silicon solar cells, and that I find quite exciting. That's not the end of the story. With efficiencies coming up, the stability and the cost, the main challenge is some of these materials are quite expensive, particularly trying to get 20-year lifetimes with organic semiconductors is probably going to be a big challenge, but it's a challenge which a lot of companies are getting excited about, and which I find quite exciting as an opportunity. I'll give you an example of that, an application a bit later. So I'm actually leading quite a large program. I should have said at the start, I've actually got 2 hats, a hat at Imperial and a hat at Swansea. And I lead this program actually from Swansea, but it's about trying to develop what we call integrated and targeted photovoltaics. So materials which can make solar cells, which are semi-transparent, which are flexible, which are light, which we can, for example, put on a greenhouse roof to absorb the infrared light and still allow the plants to grow underneath, or to go into windows, into facades. But these are all quite exciting opportunities. Anyone's interested, you can find it on that website down there. My actual research, I'm not going to talk too much about my research, but I'm actually a photochemist. I use transient spectroscopy to understand what happens when light shines on a material, and particularly on a semiconductor, and try to understand how, when the light shines on it, we've got to separate the charges to make the current, to make the solar cell work. I try and measure optically, this is timescales of, I think, picoseconds, so 10 to the minus 12 seconds. Here we go down to microseconds. Some of my measurements go out to seconds. And we try and understand structure-function relationships. So the relationship between the materials or molecular structure and how efficient the solar cell is. And my research for many, many years now has been trying to understand this connection and then help understand how to make solar cells more efficient. I'll finish this bit about solar cells by just one example. So this is an example where we were working with a company, Heliotech, in Germany, which is making a lightweight, flexible, organic solar cells, and putting them onto, in this case, onto warehouse roofing. These solar cells are made essentially the same way as you make OLED TVs and mobile phones. Many of you will have a mobile phone, and your display here is an OLED display, an organic light-emitting diode, which means that the light-emitting material in this Apple iPhone is an organic material, a molecule, which is receiving electrons, making an excited state and emitting photons. Solar cells do the opposite, using very similar materials. And these are the materials developed by this company, Heliotech. That's what's called a donor material, as a small molecule. This is a fullerene or buckyball, actually invented or discovered in the UK, which is rather exciting, where it turns out to be rather a good electron acceptor in solar cells. And my student Richard was working with this company to work out why, when they changed the temperature which they made their solar cells, then the performance changed. And then he measured lots of different dynamics of the charges separating and being collected and recombining and things, and worked out why they got better, and then went on to say what the company they needed to do if they're going to increase the performance. These solar cells are not as efficient as the silicon solar cells, yet trying to make flexible, lightweight solar cells is hard. But already there's companies starting to make money, because currently there's no competition. In terms of technology. If you want to put solar cells onto warehouse roofs, you don't use silicon solar cells. And all the current technologies, which are lightweight and flexible, are relatively expensive and relatively low efficiency, but still good enough to be useful. And I find that quite exciting. So that's a lot of what my research is doing. I'm going to just end by what I think is, for me, the big long-term challenge, which is that we're kind of understanding how we're going to decarbonize electrical power generation, but we don't really understand how we're going to decarbonize fuels and chemicals. And that's a big challenge. So our chemical industry is almost entirely based on fossil fuels. And whilst we can think about stopping using fuels, for example, in cars, it's going to be much harder to have planes which are not driven by some sort of fuel. Indeed, lorries, it's the same challenge. Ships, it's the same challenge. We're going to need fuels of some sort at still a significant scale. We also need to work out how to store intermittent power sources. Batteries are wonderful for coping with night and day intermittency of wind and solar, but batteries are not scalable. If you want to store energy, you need to build more batteries. It's far more elegant to turn the sunlight into energy stored in a molecular fuel, and put that in a tank. And that's much more scalable for, in particular, interseasonal storage, which is, I think, going to be the big challenge. We also are going to need to work out, if we start to power our world with renewables, with wind and solar, then for wind and the sun is not always where demand is. And we're going to need to ship energy, renewable energy, around the world on a large scale. And we can think about that going down to superconducting wires and all this sort of thing, but that's expensive. My own vision is we're going to be shifting energy around the world in tankers. It's just those tankers are not going to be full of crude oil from under the ground. They're going to be filled with fuels synthesized from the sun and the wind, and maybe nuclear power. And I find that all quite exciting. It's a big challenge. We can't do it yet in anywhere near competitive levels. And we need to do it cheaply and scalably, which means you need to think about rare earth elements and all this sort of thing. This is one picture of how you can imagine this. And the essence really is we're going to need to find ways to either take renewable electrons or directly take sunlight and use it to drive chemistry. This is the area of electrochemistry or electrocatalysis, taking renewable electrons or renewable electrons from the photons and drive the chemistry, for example, of making green hydrogen or green ammonia or green hydrocarbons. This is another example of motivation. It's the idea that batteries have pretty low energy densities compared to fuels, and that's why we really are going to need to get fuels. Another idea is the idea that we can have a carbon neutral cycle, where it's the idea, rather as plants do, you take CO2 from the atmosphere, you reduce it to a hydrocarbon, you then use, for example, methanol. You then use that methanol as a fuel. You may end up burning it, or you may end up turning it into something useful. If you burn it, the CO2 goes back into the atmosphere, but at least that's carbon neutral. And that's a big step forwards compared to current technology, our current fossil fuel pathways. Another way of saying this is we want, as I said, green hydrogen, green ammonia, or we want to store the sun's energy in liquid fuels. We want liquid sunshine, and I find that quite exciting. There's now a huge amount of research globally and indeed at Imperial at how we can do that. The simplest way is to wire up solar cells to some sort of electrolyzer or electrochemical conversion system, which either splits water into hydrogen and oxygen and makes our green hydrogen, or reduces CO2 to something useful or oxidizes something useful. That's exciting, but currently solar plus electrolyzers, PV plus electrolyzers is too expensive. It's probably the only way we're going to go for the next 10 years because these technologies exist. We can combine them, and people already are starting to combine green solar cells with electrolyzers to make green hydrogen. I'm interested in thinking about other ways we could put things together. And actually what I'm most excited about are just semiconductor particles. So these are materials with a valence band and a conduction band. You photo-excite them and you make electrons and holes and you drive chemistry on the surface. For many, many years, no one thought this would work. Essentially because this chemistry on the surface is slow and hard. And most of these electrons and holes, and for most materials, 99.9% of electrons and holes simply recombine in that material. And it was felt to be, if you could get it to work, it could be rather nice and very cheap, and you can have a very simple system to do it. But can we get it to work? So this is the idea. This could be the cheapest, but the efficiencies need to go up a long way. This already exists, but it's currently too expensive. Green hydrogen hydrogen gets a lot of press and excitement, some good, some bad at the moment. It's not a silver bullet, but it is likely to be a key part of our energy pathways going forwards. But nearly all hydrogen currently comes from methane. And when it's made, you release CO2. And that's not a good idea, fairly obviously. But people start to get excited. So this is an example of photocatalyst sheets. I'll show you. So this is demonstrated at 100-meter scale. Is another picture of it. These are made up of small particles of a relatively cheap semiconductor with some catalyst on the surface. And when people shine light on it, then it splits water into hydrogen and oxygen with pretty much 100% quantum efficiency. So every photon incident turns into splitting water into hydrogen and oxygen. This was published 5 years ago. I think until it was published, no one believed it was possible. This is a relatively straightforward technology. It's screen printed. Those of you who know their art. The fabrication process, you make the particles, you screen print them onto frosted glass, and you make these panels, which then you flow water over, and you make the hydrogen and the oxygen, and the hydrogen and oxygen then gets collected in this unit here, and it is split into the hydrogen and oxygen, and the hydrogen stored in a tank. That was pretty surprising and quite exciting. The challenge here is that rather obvious from the colour. Silica solar cells are black, so they absorb lots of sunlight. These sheets are white because they only absorb UV light. You can see the spectrum here. It only works with UV absorbance because it's a wide bandgap semiconductor, which means the efficiency is less than 1%, which means it's not yet commercially viable. But there's now a huge amount of research trying to work out if we can take this concept and develop materials which absorb visible light to do the same chemistry. And I'm just starting to get excited that we're finding materials which can achieve this. And I've got data now. So this is more my world of photochemistry, of kinetics, where what we have found is that what we assumed is that when we excite most of these materials, electrons and holes would disappear in nanoseconds, picoseconds, not much longer. But these are optical data we're getting on materials like this, where we are shining one sun on a sample and turning it off and seeing how long the charges live to drive the chemistry. And the chemistry of water splitting is really slow. It's a difficult catalysis. These timescales are seconds, which means you shine light on the material and the charges live for seconds. And these are cheap, simple materials. And I, as a photochemist, never expected that. I'm quite excited. These are these UV samples which work but are not so useful. These are visible samples. These are visible absorbing. It's a different semiconductor. And it turns out that you can actually make oxygen. OER is oxygen evolution reaction, simply by controlling the structure of the particles. If you facet them, if you control the surface energies of these particles, the efficiency can go up by orders of magnitude. By 2 orders of magnitude, and we correlated that with these particles now being able to separate the charges and have charges again which live for tens of seconds with quite high yields of these charges as well, which is also exciting. And it's all to do with how you control material structure. You synthesize the material, so you expose certain facets, and different facets have different energies which take the electrons and take the holes, which is quite exciting. And the nice thing here is this is potentially cheap. It's not yet good enough. It's not yet stable enough. These samples are rather unstable, but it's I find it quite exciting. We've also now started to look at organic semiconductors, which are these ones which have been used in these solar cells. These are actually a polymer and again, actually a fullerene acceptor. And really no one had expected these to work. These are rather nice because these can absorb right out into the near infrared. So you can absorb all the photons out to a long way in terms of energy. And again, these are making long-lived charges. Again, no one expected it. It turns out that you make the long-lived charges simply by exposing these semiconductors to water. And there's a change in dielectric constant between the organic and the water, which stabilizes the charges on different places on the surface. No one had thought of doing that before, but they work. And that's, I think, quite exciting. None of these are yet commercial. But I find the idea that by developing, and none of these are developed by me, I should say, we've just been measuring why they work and indeed why most materials we are sent don't work. But as a photochemist, I get quite excited about that. So this is just a kind of summary of what I've been talking about. That currently, this is where we are with solar. We are mainly putting out solar cells in fields. We are sometimes putting solar cells on to buildings. That's of course exciting, and it's driving a transformation. And when these solar cells go out into the desert or whatever, then we can generate an awful lot of power, and that's exciting. I'm more interested in the challenge of, can we have what we call integratable solar cells? solar cells which can be integrated into the built environment. These are actually some solar cells integrated into solar-powered buildings in Swansea. They're essentially laminated as a flexible technology on steel roofing. These buildings are solar powered. In Swansea, which is one of the wettest and unsunny places in the UK, so certainly not one of the sunniest places in the world. And what's even more interesting is that these buildings weren't expensive. There's a lot of discussion about how you can have zero emissions buildings. They nearly always are expensive. These are not expensive if you design them right. And that I find quite exciting. This is another example of semi-transparent devices to make into windows. When we think going forwards, so this is kind of happening now, but not yet at the big scale. But the companies already are making these devices, so at least they are commercial. And I would hope that these will expand in the next 5 years. When we look longer term, then the idea of just very simple printed foils of devices which we can print cheaply, which can hopefully get more efficient. The small area devices now of these printed foils are 20% efficient, almost the same as silicon, but just not yet cheap enough and stable enough. Or we can think about harnessing the sun, not just to make electrons, but to make fuel, which essentially is doing what nature does, but trying to find it in ways where we're achieving it with efficiencies significantly greater than nature can achieve, and therefore generating significant amounts of energy without competing with our biomass for food production. So that's what I wanted to say. I think I'm about on time, David. I'm just finishing with acknowledging I didn't show so many results, but the results as I showed came from my research group, which I'm always wonderfully grateful to. If you want to know more details about my research, then you can find it here in my Imperial website. We have a research centre which I've led for many years. I've actually just stepped down now, but looking at the whole challenge of processable electronics, which is essentially about printable semiconductors and how we can harness those for solar, but many other things as well. If you're interested in those buildings, then you can go to this site, which is a centre in Swansea I work with, and then there's some other examples of centres in the UK and in the EU, thinking about the challenge of making fuels from sunlight and chemicals from sunlight. And with that, I think I'll stop there, David.
Thank you very much, James. I think it was a very positive talk. I mean, there's so much doom and gloom. It's absolutely wonderful to hear progress being made and ideas for the future, even if they don't work yet, but you somehow have the feeling they will.
Well, I'm an optimist. Yeah. I'm aware not all things. I think science is about creating the possibilities. I can't promise that anything I showed is really going to be scalable and be a major global success story. But as a scientist, I'm interested in the art of what might be possible and seeing what for the future and creating possibility.
Well, I'm sure that matters to all of us, actually. I think. Thank you very much. So, questions. Let me. First question was from Alan Gilbertson. Alan, are you present? You can be unmuted and ask your question, or I'll read it out for you.
I'm happy to read it, myself.
Yeah,
well, it was very interesting to see how somebody had seen all the things changing over the years progressively, and we didn't have long to look at that graph. There's a lot on it. I was just struck by the way coal had shriveled away quite quickly.
Of course.
And thought how that might happen.
So of course that's a projection, and it's not my projection. And how rapidly coal drops off is of course significantly down to politics. What I find exciting though is that even with current prices, solar is now very often cheaper than coal for making electrical power in sunny places.
Yeah.
And if China is the obvious grand example, where of course they're still building coal-powered power stations, but they are growing their solar technology so fast. And it's just that projection was just about if we continued on the historical pathway of where solar is going, exponentials have a habit of taking over. Of course, whether that happens and everyone, and that's a projection, and if you were more cautious, you would assume that solar is going to saturate in the next couple of years and stop growing. But people have been saying solar is going to saturate in the next couple of years for the last 10 years, and it's never saturated.
Yeah. I'm not
So
really
I don't have an
surprised.
answer to your question.
Yes, it does. Thank you. As you say,
Yes.
there's a lot of politics and economics in play as well. We've got a friend who's always saying about they've got tiles in California that can produce energy, and they put them on buildings, and why haven't we got them here? So you might know the answer to that question.
Well, it's about how you put them onto buildings. We have the same technology here as we have in the US. Well, it depends where it's made, but the problem currently is that almost all PV devices are these silicon cell between two plates of glass, and you can stick that onto a building, but it's harder to integrate into the building fabric. There is now a transition. It's not just these organic and perovskite cells, there's other thin film technologies, and silicon starting to get a little bit better. But of where you can, the solar cell is the roof.
Yeah.
Or it is the window, and that changes the economics.
Well, I mean, tiles are particularly stiff anyway, so you don't have to worry about them bending.
Yeah. So there have been solar-powered tiles in the UK, but currently they're not that so efficient. The problem is that all the technologies which are more flexible and easy to put on a tile or whatever, they tend to be less efficient. And so they are niche applications at present. The hope is they're going to become larger scale as the costs come down and efficiencies go up.
Right. Okay. Thank you.
Okay.
Give way to more technically qualified people now. Thank you very much.
Thank you. Brett Sanderson. Brett, would you like to speak up?
Sure. So, James, nice to see you again. It was
Yes,
17 years ago that you vivored me, and I have to confess, like being in finance, I haven't really kept up with what was specifically going on in my field of research. So, question for you about organic molecular thin film solar cells, like the Stephen Forrest research. We were, massively sort of bigging up his up to 2% efficiency cells 17 years ago, but I just wondered where that has gotten to over the past sort of 15, 17 years. And obviously we were super aspirational about that being commercially viable, but I've not actually seen any of that out in the wild yet.
So you're quite right. 17 years ago, 2% was the limit for organic solar cells. And most people were predicting that 10% was the limit, maybe 12% or so. I think this year, organic solar cells passed 20%. And that actually change in efficiency from 10 to 20% has been in the last 5 years.
Wow.
Quite apart from predictions of economics, predictions of performance have significantly underestimated where we're going to get to. I think 5 years ago, people would have said it would be impossible to get organic solar cell at 20%. It's already been done. And there's currently no sign of it stop. I guess it will limit about 25 because that's where the thermodynamic limits are, or something like that. We're going to have to find a limit at some point, but that's quite a big transformation. That's so far all primarily in solution process devices. Evaporated have had far less research. The Heliotech, the company I mentioned, is commercial. It's been going about 10 years now. Its commercial cells are about 8%. I think with a triple junction, it gets up to 10%. That's not yet enough to be for large scale deployment, but they've been in manufacture for 10 years, which is quite impressive.
Interesting.
They're in roll-to-roll evaporated manufacture.
That was always the sort of quick and dirty way, was the sort of solution processing versus what I would say was the purer way of like molecular beam deposition. But it's interesting that what the sort of quick and dirty has taken off over the purer form?
It depends on the so one of the problems is that to evaporate, you need to invest more money in the research lab. A spin coat is very easy, and the evaporators are more expensive. For companies that's not to scale, it's not such a big issue, but for the small research, it means there's actually not much research on evaporated solar cells. Lots on these OLEDs but I actually think evaporated organics is an understudied field.
Cool, thank you.
Okay, thank you, Brett. Asma, would you like to speak?
Hello.
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 Yes.
Good afternoon.
Yes.
Hello, good afternoon. I'm fascinated by your talk. I'm really taken by the chemistry bit of it.
Oh.
I would just like to know where is the solar technology fully in action right now?
You mean in
In
deployment?
Britain or in any part of
manufacture?
the world?
Well, if you drive down a motorway in the UK now, you'll find fields of solar cells, or maybe too many fields of solar cells, at some people's viewpoint, all over the place. The dominant solar deployment and solar manufacturers in China. Almost all. We can argue about the politics of this and why the EU allowed their developing PV technology to disappear. And manufacturing and all move to China, but China does dominate silicon solar cells, and China is also by far the dominant country deploying solar cells, mainly in the west of the country where there's lots of space, and they already have a challenge now about how they're going to get that energy from the west to the east of their country where the demand is.
Thank you.
Does that answer your question?
Yes, it does. Yeah.
Of course, in any other country, I've actually worked a lot with. Yeah.
Yes, I mean, it's fascinating to learn that China is so advanced in this technology, and yet they're also building coal-fired power stations. I assume that's just because they have such a big population, is it?
I think it's mainly limited by how quickly they can grow the silicon. So
yeah, okay.
They're building silicon fab lines for the solar cells ridiculously fast. But every 3 years they build the equivalent of all previous silicon manufacturing plants. But they started very small, and so and China uses a lot of energy. So solar is now the dominant energy technology in terms of investments beyond beyond coal, beyond anything. It's got a long way. It started off small and it's still growing.
Fascinating. I'm going to take so many things home from this talk. Right, Alan, would you like to put your question? You need to unmute, Alan. You're still muted.
I can read your question.
Well, we can read it. Yeah. Super talk. Could you please summarize the merits of organic versus perovskites? Okay. You probably should tell us first what perovskites are. I think I know, but I suspect one or two others don't. So
this refers to the semiconductor which is absorbing the photons. And either we use an organic semiconductor, or there's a new material, a perovskite. It's a kind of sleight of hand. The word perovskite formally means a particular crystal structure which was developed for a crystal, was found for a crystal in a geological crystal in I think in Russia some 100 years ago.
Yeah, that's right. It was discovered in 1876, I think. You
know better than me,
in
Dave.
The Urals.
Yes. But there's a particular form of perovskite structure which is an organic inorganic hybrid. So where one of the cations is an organic cation and the anion and one of the other cations is are inorganic. And it turns out that this particular organic inorganic hybrid perovskite. A, you can print it from solution, which is quite exciting, and B, it makes surprisingly good semiconductors, which make surprisingly efficient solar cells. And this is a relatively new discovery, but they really took off about 13 years ago. The UK is one of the leads in the development of this technology. Oxford PV is one of the leading companies trying to turn this into a commercial product. Organics were trendy until about 10 years ago. Then fashion changed, perovskites came along, they're very exciting. Their efficiency is now at about 27%. Organics are having a bit of a renaissance because their efficiencies have jumped up because people have found actually alternatives to fullerenes as acceptors in these materials, so what we call non-fullerene acceptors, which is a really boring term, but yeah, that's what we do. Which is going to be more useful? I don't really know. They have different advantages. So organics are not as efficient yet, and I don't think ever will be so efficient. They can be stable. Helitech has devices which live for have been shown commercially to live for 10 years or something. You can make them semi-transparent. You can change the color, this sort of thing. Perovskites have the efficiency advantage. They also have mobile ions in them, and that makes them potentially unstable. And trying to understand the impact of those mobile ions on stability is currently kind of an unsolved problem. There's lots of arguments, and of course, the companies now commercializing will tell you they've solved the efficiency, the stability numbers. Oxford PV has just shipped its first commercial product with I don't know exactly what they guaranteed for stability, but of course, guaranteeing silicon cells have a 25-year lifetime. Guaranteeing a 25-year lifetime with a technology which has only been around for 13 years, and where the devices you're making have been around for 1 year, is quite hard.
Yes, I think the test is an interesting test you would do to prove it. But anyhow,
there's also issues that perovskite cells, the inorganic cation is nearly always lead. That has significant toxicity issues.
It's not a very pleasant substance. No,
it's not much lead. So it's actually, I think, more lead in silicon solar cells than there is. But it's unfortunately, the lead in the perovskite cells is a soluble form of lead, which is less ideal.
Okay, Sir Peter Michael. Sir Peter, would you like to speak? Yes.
Yes, speaking is probably best in the pose I am of the Sunday here. Would you mind not answering all the questions I ask ahead of me? You're catching up with me. I have a young 20-year-old grandson here who wants to know about the practicality of solar cells on warehouse roofs.
Oh.
I was more interested in you briefly you went over it quite quickly, the solar cells in housing, and
yes,
why it brings costs down so much. Is it because they're being used structurally?
There's two issues. One is that currently, to put solar cells on your roof, the main cost is not the solar cell, it's putting it on your roof. And if we can find ways to reduce the cost of the installation by, for example, the solar cell being the roof when you need a new roof, that brings down the cost. The other is that if, for example, you wanted to put silicon solar cells on warehouse roofing, or actually those buildings I showed you in Swansea, then you'd have had to build bigger steel girders to hold up the building. And if you can, because the solar cells would be too heavy, if you have a lightweight solar cell, then you can use the existing structures of a warehouses and put the solar cell on top. And so, for example, those builders I showed you in Swansea, can you still see my screen? I don't know.
Yeah, we can.
I dropped the slide, so
yeah. So if I go back to these buildings I showed you a minute ago,
yeah,
the buildings, forgotten where I showed them. these buildings, actually, I don't really talk about them very much. So these are covered by actually a flexible SIGS technology, which I don't think is going to be scalable, but it was interesting. But the point is that they wanted solar powered buildings. The SIGS solar cells are less efficient and more expensive than the silicon. But if they had covered them in silicon solar cells and made the buildings stronger, overall the cost would have been higher, because it cost a lot more to make the building strong enough to carry the silicon solar cells. Does that answer your question?
Yeah, yeah.
I think that's fascinating. I mean, I'm not entirely pleased to learn it, but there you go. Okay, you've got some more questions, at least under the heading, Sir Peter Michael. Are multi-layers practical? And then there's a reference to the Morocco X project, which I don't know what that is. So do you want to say anything from the questioner's end?
Well, yeah, that's the project to build 10 square miles of silicon solar cells in the desert in Morocco and transmit the electricity 2,500 kilometers to Devon.
I've actually got, funny enough, I've got some slides on almost the same thing. But so I can't, I'm not expert enough to comment on the cost of electrical wiring. There have been various arguments about how we can use the essential problem is with moving electrons by wires large distances, you get large IR losses, resistance losses. And so you need a very low resistivity or resistance of your wires. You need a high voltage, and that adds a lot to the cost, which is essentially why it hasn't happened yet. Whether those costs are going to come down, whether the cost of the cabling and the energy loss by making those distances low enough will happen, I can't tell you. All I can tell you is I've been hearing recommendations or exciting plans about solar cells in the Sahara and the cables being electrical power to Southern Europe or to the UK for some 20 years, and currently they haven't happened because of those costs. This was analysis I quite liked, which was not, again, actually targeting Morocco. Funny enough, it was actually looking at Belgium and how much energy Belgium needed, and the idea it's going to need to import renewable energy. And their plan was actually, which was actually put together by Energy, an energy company in France and Belgium, where they were going to use solar cells to electrolyze water, and then actually use the hydrogen from the electrolyzer to reduce CO2, and then reduce the CO2 to make a methanol, and then put it in their tankers and bring it to, in this case it was Belgium, but we could do the same thing for the UK. And in general, that actually, in terms of energy efficiency, that was surprisingly efficient. I think it was, overall it was, I forgot what the number was, but about 10% efficient getting the energy from the sun to Belgium. The biggest cost factor actually was the direct air capture, where you're going to get the CO2 from. And that's actually why it's not happening yet, because we don't know where to get the CO2 from. I'm quite excited about doing what plants do. Plants use the sun's energy to capture CO2 from the atmosphere. And currently no one's really doing that, and I find that quite exciting. So that's not quite an answer to your question, but it was just, well, maybe it's a different answer to your question. I think
that's by far the most exciting potential that there is. The plant efficiency is down at 1 or 2%, I think.
Exactly.
And if you could raise it to 5 or 6%, boy, that would really change things in a big way.
I don't think that's going to happen in the next 5 years, but I would hope in the next 10 to 20 years that's going to happen.
Most exciting talk, thank you.
Okay. Well, I'm going to read the last question I can see from, it's not a question, it's a comment from Rob Williams, and I see that he doesn't have a microphone, and he's actually emphasizing the point that in 2016 he put 50 kilowatt solar panels on a 1950s tiled roof, and then last year had to fit scaffolding to remove them.
Yes, of course.
Simply because it was the roof was needed replacing. I don't think there's any comment needed from you, James, because you've more or less given us similar warnings. It's just a credibility is added by experience, and it's something we all need to think about. I think actually your timing has been meticulous. You've kept them talking, and you talked for exactly the right amount of time. And now we're at the time when I have to, first of all, say thank you for a very invigorating talk. I really come away with all sorts of things going round in my mind that I half knew. And I feel it's really been an excellent update on where we are. And there are so many more questions that I think we'll have to have you back in a few years' time, because it'll be a different talk, I'm sure. Anyhow,
yes.
I'd like everybody who can turn on their mics or indeed you can use a symbol somewhere down below to express our positive appreciation of an excellent talk by Professor James Durrant.
Yeah.
Thank you very much, James.
Very good.
Thank you.
Thank you.